Hello friends, how are you? Welcome to my channel Crazy Maths Made Easy. Today I am going to discuss the chapter 1 of 10th Maths, that is real numbers. Here I am going to explain a series of classes about 10th class maths. In that series, let us see the first chapter, real numbers. Okay, what is the real numbers, friends? Real numbers is a system of numbers which is having so many combination of numbers. That is, here if you see the diagram, real numbers means it is having natural numbers and whole numbers, integers, rational numbers and irrational numbers. All these including will get the real number system. The natural number means 1, 2, 3, 4 like that, all the digits. And whole numbers means if we add 0 to natural numbers, we will get the whole numbers. Integer means if we add negative numbers to the whole numbers, we will get all integers. And rational number means the numbers which can be written as a by b form, where b is not equal to 0, are called rational numbers. That is, all fractions comes into rational numbers. And irrational numbers means the numbers which cannot be written in the form of a by b. Okay, the numbers which cannot be written in the form of a by b. That is like root 3, root 4, root 2, root 15, like that, pi, like that. All these numbers comes under irrational numbers. So all these rational numbers and irrational numbers, all including, we will get the real number system. Okay. Next, we will see what are the concepts we are going to cover in this real numbers chapter. Okay, these are the concepts we are going to cover in real numbers. That is, first introduction concept, what is real numbers and what are the theorems we will get in real numbers, how the real numbers work, like that concepts we will see in introduction. Next, we will see the fundamental theorem of arithmetic. This is one of the theorems which is usually used to calculate all the real numbers problems, that we will see. And what is the fundamental theorem of arithmetic and the proof of that theorem, and what is LCM, least common multiple, HCF, highest common factor, by the factorization method, how to calculate this, and the related problems also we will see. All the problems and examples I will explain here very clearly in a simple way. In next topic, we will see revisiting the rational numbers. Okay. Actually, this fundamental theorem mainly depends upon rational numbers, and in the next concept, we will see the irrational numbers also. In irrational numbers, we will see the theorem, one more theorem here it is there. Let p be a prime number. If p divides a square, then p divides a, where a is a positive integer. So here this is the theorem. If a square, p divides a square, then p divides a also. A square is divided by p, then a also divided by p. That is the theorem. For that proof also we will see. And next, one more theorem. Root 2 is irrational. Root 2 is the main prime number and first prime number in the total numbers. So, 2 is the prime number and root 2 is the first irrational number. So, we need to prove root 2 is the irrational number. Depending upon this proof, we will get the other numbers, irrationality also we will prove. Okay. So, in this also we will see the problems and examples of irrational numbers, everything we will see. And finally, we will see summary, what are the topics we covered, all the things we will see. Okay. Listen carefully, friends. The introduction. Here, introduction, we begin with two very important properties of a positive number. Okay. We have two properties for the positive number. That is, one is Euclid's division algorithm. It says any positive number a can be divided by another positive number b in such a way that it leaves a remainder r that is smaller than b. Understood? Once again I will say, it says that any positive integer a can be divided by another positive number b. That means here a by b. Okay, in such a way that it leaves a remainder r. That means if we divide b, if we divide a with b, we will get some value, some x we will get, and it leaves a remainder r by giving some coefficient, suppose c. Okay, and that is smaller than b. This r is always smaller than, so r is always smaller than b. Because if r is greater than b, then it is once again divisible by b to get smaller than b. Understood, no? Suppose here 12 is there. Now we are dividing with 5. So 5 2s 10 2. So we will get the remainder 2 and coefficient 2. So we divide 12 by 5, we will get the remainder 2. This remainder is smaller than 5. Understood, no? This 2 is smaller than 5. If we got more than 5, that is suppose here 20 we get, means once again we will divide it. 5 4s 20, here 0. So what we will get? Always less than this 5. Remainder always less than this 5. It is 0 or anything which is always less than this 5. Same thing here he explained. It says that any positive integer a can be divided by another positive integer b, that is a can be divided by another positive integer b in such a way that it leaves a remainder r that is smaller than b. It leaves a remainder r that is smaller than b. If r is equal to 0 means it is perfectly divisible. If r is not equal to 0 means it is not perfectly divisible. It will get a remainder. In this example, if you see here 12 is there, 5. If we divide 12 by 5, we will get the remainder as 2. 12, 5, 5 to 10, we will get the remainder as 2. So 2 is always less than 5. That is the theorem what Euclid's division algorithm says. Suppose if we take 25, 5 4s 20. So here remainder is 0. Here in this case 20 is perfectly divisible by 5. We will get remainder as 0. In this case we will get remainder as 2. So in any case, if a is divided by any positive integer b in such a way that it leaves a remainder r that is smaller than b, that is r is smaller than b always. This is generally we know, but it is defined firstly by Euclid's. That's why it is called Euclid's division algorithm. So this Euclid's division algorithm, here we have some applications, that is divisibility of property of integers. That means if a number is there, how it is divisible by 2, how it is divisible by 3, how it is divisible by 5, like that. What is the divisibility property of the integers? For that, by using this Euclid's division algorithm, we will calculate. Next, HCF of two positive integers also we can calculate by using this division algorithm. How to calculate HCF? Suppose HCF of a comma b is there. How to calculate it? We will write first, if b is bigger than a, we will write a and we will get some x and we will get c, and once again c we will divide with a, some y, that we will get like that. Like that we will calculate to the maximum possible extent to get 0. Okay, to get remainder 0. Like this, by using Euclid's division algorithm, we can calculate a HCF of two positive integers. Next, fundamental theorem of arithmetic. This is the another theorem which we used in real number problems calculations. It states that every composite number can be expressed as a product of prime numbers in a unique way. Okay, here we have two types of numbers. One is prime number, another one is composite number. Prime number means the number which is having one and same number as its factor is called a prime number. That means suppose here 2 is there. 2 is having factors of 1 and 2. That means 1 and same number. 3 is there. 1 and same number. 5 is there. one and same number. So all these numbers having one and same number as its factors. So 2, 3, 5 like that, these type of numbers are called prime numbers. Composite number means the number which is having factors other than the number and the 1 also. That means other prime numbers also are factors of that number. Suppose here 12 is there. 12, what are the factors? 1, 2, 3, 12, 6, 4. So these are the factors of the 12. So apart from 1 and the same number 12, it is having another factors 2, 3, 6, 4. All these are factors of 12. So in that case, this 12 is called a composite number. It states that every composite number can be expressed as a product of prime numbers in a unique way. So what is this theorem says? This 12 can be written as product of primes in a unique way. Product of primes in a unique way. Product of prime means here we have 1 and 2, 3, 4, 6, 12. So in this, what are the prime numbers? 2, 3. 2 and 3 are the prime numbers. So by using 2, 3, we will get the 12. How we will get? 2 into 3. So 2 square into 4 into 3 means 12. So what he is saying is, any composite number, it is having several factors other than one and the same number, and in a unique way it can be represented using prime numbers only. Okay. So here 12 is equal to 2 square into 3, where 2 and 3 are the prime numbers. Like this, every composite number can be expressed in product of the prime numbers, okay, in a unique way. Okay. Factors means if we multiplied with 2 by 3, we will get 6 factor. If we multiplied with 2 by 2, we will get 4 factor. Like that, factors we will get any factors. But the expression with respect to the primary numbers, that means it is having primary numbers as the factors, that is in this form only. The order can be changed, that is we can write 3 into 2 square, or 2 square into 3, or 2 into 2 into 3. Okay, whatever may be the form, we will get only 2 and 3 as the prime factors of 12. Other than that, no other prime factors exist for the 12. Like that, what is the fundamental theorem of arithmetic? It states that every composite number can be expressed as a product of the primes in a unique way. Okay, understood now? So by using the prime numbers, we express a composite number in a unique way. That means if a composite number can be expressed in a set of prime numbers, only that set of prime numbers only exist for that composite number. No other prime number is the can be come in that composite number product. Later we will explain clearly what is the fundamental theorem of arithmetic and its proof also. It is very important theorem, and I will say very simple way. Next, what are the applications for this? To prove the irrationality of a rational number. I have said previously, no, root 2, root 3, all these are called irrational numbers, and to prove the irrationality of these numbers, we use this fundamental theorem of arithmetic. Don't worry, everything I will explain in clear way. Next one, next application is to explore when exactly the decimal expansion is rational number and it is terminating, and when it is not terminating and repeating. This we will see in later chapters. Here, what is P by Q form? P by Q means rational number, where Q is not equal to 0. Always remember this point. P by Q, Q is not equal to 0 is important. If Q is equal to 0, we will go to infinite numbers. Okay, Q is not equal to 0, and we can return any number in the form of P by Q, that is called as a rational number. Okay, that rational number is terminating. Terminating means P by Q. If you write here, suppose 12 by 3, we will get 4. Okay, 3 by 9, that is 1 by 3, that is 0.33333, like that we will get. So this number is terminating. 12 by 3 means 4. We will get 4 and remainder as 0. But here 3 by 9 means 1 by 3. We will get 0.3333, like that we will get. So it is not terminating. It is not terminating form, and 12 by 3 is the terminating form. So for explaining these concepts also, we will use fundamental theorem of arithmetic. Okay, that we will see in later chapter. In this chapters we will see what is the Euclid's division algorithm we have seen, and fundamental theorem of arithmetic. Everything we will see now. So this is the fundamental theorem of arithmetic. Here Euclid's division theorem is simply everybody know. This fundamental theorem is somewhat tricky. So we will explain that concept clearly. Definition: every composite number can be factorized as a product of primes, and this factorization is unique apart from the order in which the prime factors occur. Once again I will say, every composite number can be expressed or factorized as a product of primes. That means every composite number can be expressed as a product of prime numbers, and its factorization is unique. That factorization form is unique nature apart from the order in which the prime factors occurs. That order of numbers may be changed. Okay, here I will show an example. Here you see, here 1771 is one composite number. It is having factors 7, 11 and 23. Okay, so this composite number can be expressed as factor of the prime numbers. That is the first point. And this factorization is unique. That means no other prime number can come in this picture. Suppose here 2 is not divisible by this number, so 2 cannot write here. Only this 11, 7 and 23, these three prime factors only come to 1771 composite number. No other prime factors come. So this is unique. This combination is unique, and order may be changed. That means we can write like this also: 23 into 11 into 7, or 7 into 23 into 11, like that. Like that we can change the order, but this combination is unique. 23, 11, 7. This combination is unique. That is the fundamental theorem of arithmetic. So every composite number 1771 or anything can be expressed as a or factorized as a product of primes, and this combination is unique. That is, this factorization is unique. Okay, only 7, 11, 23 are the prime factors of this number. No other prime factors exist. That is, this factorization is unique apart from the order in which the prime factors occur. The order may be changed. So these numbers we can written in any order, that is 23 first, 7 last, or 7 first, 11 last, like that order can be changed, but the factorization is always unique. Okay, understood? Here in this example also, here 5, 3, 1, 3, we have 4 prime numbers as factors: 3, 7, 11, 23. In this also we can change the order: 11 into 7 into 23 into 3, or we can take another order: 11 into 23 into 7 into 3, like that we can take any order. But this factorization, that means only these 4 are the factors of this 5, 3, 1, 3. No other factors, no other prime factors can exist. Okay, no other prime factors. Remember that point, prime factor. No other prime factors can exist. That order may be changed. Okay. Similarly here 10626, it is having 5 prime factors: 2, 3, 7, 11, 23. In this also, these 5 are the prime numbers of this composite number, prime factors of this composite number. The order may be changed, but no other prime number exists. Here we have 8232. In this we have 2 power 3. That means 2 factor came 3 times, and 3 and 7 power 3. 7 factor came 3 times. This is also only these 3 are the prime factors exist, and we can change the order: 2 power 3 into 7 power 3 into 3, or 7 power 3 into 3 into 2 power 3. Like that we can change the order. But this combination is unique. Okay. Same here also. 32760. For this we have many factors are there like this, and 1 2 3 4 5 6 7 8 9. For this also we have 3 factors are there, 3 3803 360. Here also order can be changed. This can come first, this can come second, this can come third, but this factorization combination is unique. Okay. So here we see this is called a factor tree. How to calculate factor tree for any number? First we write the number. Okay, first we write the number here, and what is the first prime number? 2. We will divide it by 2. If it is divisible by 2, then we will get this one, and once again it is divisible by 2, we will get this one. Once again it is divisible by 2, we will get this number. Here 4095. Sum of this 9 plus 4 plus 5 is 18. 18 means it is divisible by 3. So this total number is divisible by 3. Next 1365. This total number is divisible by 3. 455. This total number is divisible by next number, that is 5. Next 91. This is divisible by 7. 7 into 13 we will get 91. So by writing with the smallest prime number to other prime numbers, we will get all prime factors of this number 32760. So what we got? 1 2 3. 3 2s we got, that is 2 power 3. Okay, 2 power 3. Next what we got? 2 3s here, that is 3 power 2. Next 1 5 we got. Next 1 7 we got. Next 13. Okay, all these are prime factors of this composite number. Okay, how to write factor tree? First we take the number and divide by smallest possible prime number 2. If it is divisible by 2, then write, and next check whether it is divisible by once again 2. Next it is once again 2, like that. So up to what point it is divisible by 2, we write the 2 and the divided number. If it is not divisible by 2, then we go for other prime number, that is 3. After the 2 we get 3. So whether it is divisible by 3, we will do it. Whether next number is divisible by 3, we will do it. Till what time? Till it is not divisible by 3, till that time we will write with 3. Okay. So up to this point I got 3. Here what we got? 455. 455 is not divisible by 3. So we will check with the next number 5. With next number 5, it is divisible. So 5 I have written. Next 91. Here 91 is not divisible by 5. So I go for next number, next prime number 7. So 7 into 13, 91. Like that, from starting least prime number 2, I am doing this calculation, and finally I stopped at 30. So all these prime numbers you count 1, 2, 3. That is 3 number of 2s are there. That is 2 power 3. Next 3, 3. 2 number of 3s are there. That is 3 square. Next 1 5 is there. 1 7 is there. 1 13 is there. Like that, for any number we can write the factors. Remember this question we got in public exams also many times. What is the factor tree of a number? And they will ask this point. Suppose this will give blank number, some x we will give, and find out x, like that. Okay, that we will see in later chapters. Okay, so this is the fundamental theorem of arithmetic. What it says is every composite number can be expressed as a product of primes, and its factorization is unique apart from the order in which prime factors occur. Here from this all this explanation, what we see, this leads us to a conjecture that every composite number can be written as a product of powers of primes. That is, every composite number can be expressed as a product of powers of primes. Here 2, 3, 7, 5, 13, all these are primes. Powers 2 power 3, 3 power 2, 7 power 1, 5 power 1, 13 power 1. Powers, product, all these are multiplied. So every composite number can be written as product of powers of primes in a unique way. That means if once we have written these are the only prime factors existed for that composite number. No other prime factor can exist, because this is we calculated by using these prime factors only. Okay, in the unique way. That means only these prime factors exist. The order may be changed except for the order in which primes occurs. That means this order, this written order may be changed. 13 we can write first, 7 we can write second, like that. This order may be changed, but other than this, no other prime number can be a factor of this composite number. That is the fundamental theorem of arithmetic. Okay, understood, friends? So here this is the proof. For proving this, we can write in a systematic way. Here the prime factorization of natural number is unique, except for the order in which its factors. Okay, so this is same as the fundamental arithmetic theorem. Once again it has written here. The prime factorization of any natural number is unique except for the order its factors. In general, let the composite number be x. We will take the composite number x. We factorize it as x is equal to p1 into p2 into and so on pn, where this p1, p2 and so on pn are all are the prime factors. Okay, all are the prime factors. So where p1, p2 and pn are primes and written in ascending order, that is p1 is less than or equal to p2 is less than or equal to and so on pn. Okay, these are the prime factors. If we combine same primes, we will get the powers of the primes. Suppose for example, here we have seen 32760. For that, what are the prime factors? 32760 we have 3 2s are there and 2 3s are there, 1 5 is there, 1 7 is there, 1 13 is there. See, this factor tree you see, 2 3s are there, sorry, 3 2s are there, 2 3s are there, 1 5, 1 7, 1 13. Okay, so all these are written in ascending order. P1 is less than or equal to P2 is less and so on Pn. So all these are written in ascending order. Same numbers we multiply. That is 2 into 2 into 2, 2 cube, 3 into 3, 3 square, 1 5 is there, 7, 13, like that. We write the same all prime numbers in the ascending order and we multiplied the same prime numbers. So this is the factorization of 32760. This is the prime factorization. Okay, this is the prime factorization of 3260. This is the prime factorization. So once we have decided that the order will be ascending, then the way the number is factorized is unique. So if you return all these numbers in ascending order and this factorization is, it becomes unique. That means only possible prime numbers that are factors to that composite numbers are only this only, 2 cube, 3 square, 5, 7, 13. Other than this, no other prime number can be possible factor of 32760. This is the unique factorization of 32760. Okay, this order may be changed. That means 13 we can write first, 7 we can write second, 5 we can write third, like that. This order may be changed. Here this comes here and this goes here, like that. This order may be changed. But other than this, no other prime factor can be a possible factor of 32760. Okay, understood? This is the proof of fundamental theorem of arithmetic. Okay, and here we have LCM and HCF by factorization method. What is LCM? LCM is nothing but product of greatest power of each prime factor involved in the numbers. And what is HCF? HCF is product of the smallest power of each common prime factor in the numbers. So LCM means greatest power of each. Everything we need to consider. HCF means smallest power of each common one. Okay. We will see with examples. Then we can know very well. For any two positive integers a and b, HCF of AB multiplied by LCM of AB is always equal to the product of that number A into B. This also we can see whether it is correct or not, we can see with the examples. Here we have some explanation. 6, 20 numbers given. With 6, 20 numbers, we can calculate LCM and HCF, and we can prove that HCF into LCM is equal to A into B. Okay. See here, given numbers, what are that? 6, 20. Okay, in this we need to calculate LCM. Here I will calculate LCM by using the factorization method. So for 6 I write the factors. 6 is equal to 2 into 3. Here I write only primary factors, because for calculating LCM and HCF we write the primary factors only. And for 20, what we will get? 2 into 5. Here it is, for 6 it is 2 power 1 into 3 power 1. For 20 it is 2 power 2 into 5 power 1. So from LCM definition, what it says? LCM is product of greatest power of each. Greatest power of each prime factor. Okay. So here greatest power means, here we have 2 power 1 is there and 2 power 2 is there. What is the greatest? 2 power 2 is the greatest. So first point we write 2 power 2. 2 power 2 multiplied by. Here the greatest power of each prime factor it has written. So each means here 3 is there, here 3 is not there. So if 1 is not there also, we write what is present. So 3 power 1 we need to write. And 5 here it is there and here it is not there. So we write here whatever present we write there. So we will not omit anyone. That is, here 2 is, if both are exist means in both numbers that factor exists means we take the greatest factor. That is 2 power 1, 2 power 2 means we take 2 power 2. If one factor is not exist means whatever the exist factor we write same way. Okay. So here LCM is equal to 2 power 2 into 3 power 1 into 5 power 1, that is 4 into 3 into 5, that is equal to 60 is the LCM. Understood, no? So here we need to write each power of each greatest power of each prime factor. That means each means whatever the prime factors exist in these two numbers we need to write. If any prime factor is repeating in both numbers, that is here 2 is repeating in both numbers, simply we write what is the greatest. That is here 2 is there, 2 power 2 is there. 2 power 2 is the greatest, so I write 2 power 2, and 3 and 5 are only present in one number, so I need to include those two. Next, write what is HCF. HCF is equal to common smallest power of each common. 2 into 5. This is for 6. This is for 20. 2 into 3 for 6. 2 power 2 into 5 for 20. So here HCF definition, what is it saying? Smallest power of each common factor. It is taking only common things only. Non-common things it cannot be considered. So 3, 5 are not common things. So these two it will not consider. Only what is common it will take. And in that common also smallest power only it will take. That is 2 only it will take. So HCF is 2. Because here in 2 comma 2 power 2, what is the smallest? Smallest is 2. So only 2 you will take. So HCF is only 2 and LCM is 60. Okay. From 6 comma 20 numbers, LCM is 60 and HCF is 2. Now I will check this formula whether it is correct or not. What is HCF? HCF into LCM is equal to 2 multiplied by 60 is equal to 120. And what is product of numbers? A into B. A is 6, B is 20 is equal to 120. Okay. So here 120 and product of HCF and LCM also 120. So from this we can write HCF into LCM is equal to product of the number. Okay. So this is LCM and HCF by factorization method. LCM is product of the greatest power of each prime factor. Always remember this. This is very important. Greatest power of each prime factor. That means we need to take each factor, and if any two factors are common in both numbers, we need to take greatest power of that common factor. Here we have 2, 3. Here we have 2 power 2, 5. So 2 power 1 into 3 power 1, 2 power 2 into 5 power 1. Here we need to take each common, each factor. That is, what are the factors we have in both numbers? 2, 3, 5. So we need to include all factors 2, 3, 5. If any factor is common, we will take highest power of that common factor. Here 2 is common in both numbers. So what is the highest power of 2? That is 2 power 2. 2 power 2 we write. For calculating the LCM, we need to write we need to write each prime factor, and if any prime factor is common in all the numbers, then we need to take greatest power of that. And an opposite to that, HCF, what it will take? It is smallest power of each common factor. Okay, each common factor. That means it will take only common factors. That means here we have 2 into 3, here 2 into 5. What is common in both numbers? 2. So we will take only 2. In that also, what is the smallest? 2 or 2 square. What is the smallest? 2 is the small. We will take the smallest value. Okay, understood? Like this we can calculate LCM and HCF by factorization method. Okay. So what we have seen here, first we have seen the fundamental theorem of arithmetic, that is every composite number can be expressed as a product of primes and its factorization is unique apart from the order in which the prime factors occur. That means every composite number is represented only one possible way of factors of a prime numbers. Okay, the order may be changed, but no other prime factors cannot be included. What is other than written in that? Okay, so I have explained that clearly previously, and proof also we have seen, and LCM and HCF by using the factorization method, and this example also we have seen. These points you remember, LCM is always greatest power of each prime factor. HCF is always smallest power of each common prime factor. Okay. So next we will go to the problems. Here every problem I will explain clearly. So see here, consider the numbers 4 power n, where n is the natural number. Check whether there is any value of n for which 4 power n ends with a digit 0. Okay. Once again I read the problem. Consider the number 4 power n. Okay, where n is a natural number. What is given number? 4 power n, where n can be natural number means 1, 2, 3 and so on. Any number is possible for n. Okay, check whether there is any value for n for which 4 power n ends with digit 0. That means if we substitute 4 power 1 is equal to 4, it ends with 0? No. 4 power 2, 4 square 16, it ends with 0? No. Like that, for any possible value of n, whether the 4 power n could be end with 0. That means here instead of 6 or 4 we will get 0 for any possible value of n. We need to check that. Okay. So what is the first condition to get 0 as end digit if any number is there? 4, 5, 6, 0. To get 0, what is the possibility? It should be multiplied with 5 or it should be multiplied with 0. Okay, understood now? If it is multiplied with 5, we will get 0. That is 2 into 5 or 4 into 5, we will get 0. Or it is multiplied with 0, we get 0. Okay, here in 4 power n, what we will get? If for any n we get 4 or 4 into 4 or 4 into 4 into 4 3 times. Like that only we will get. Okay, so to get 0, it should be multiplied by 5. Then only we will get 0. Okay, 4 into 5 is 20. Then only we will get 0. So 4 power n to be having last digit as 0, four power n should have five as its factor. Okay, so to get 4 power n having last digit 0, we will get 4 power n should have 5 as its factor. If 5 is the factor of this 4 power n, then 4 into 5 multiplied, we will get the 0 as its last digit. But is it possible that 5 as factor of 4 power n? That we will see. So what is 4 power n? 2 square whole power n. Okay, so 2 power 2n. So this is the factorization of prime factorization of 4 power n. This is the prime factorization of 4 power n. So what it is contained? Only 2 as prime number. 2 power 2n means only 2 prime number is the factor of 4 power n. So what is this theorem says? Fundamental theorem. What it says? It can be written as any composite number can be written as factors of a prime numbers in a unique way. That is 2 power 2n is the unique way representation of this composite number. Unique way means no other prime factor exists other than 2 for the composite number 4 power n. What it means is 5 is not a factor of 4 power n. Okay, understood no? So 4 power n is a composite number. It can be written as 2 power 2n. This is the prime factorization of 4 power n. From the fundamental theorem, here we obtained 2 as the prime factor for 4 power n. So by uniqueness of fundamental theorem, what we say, no other factor other than 2 can be a prime factor for 4 power n. So 5 is not a factor of 4 power n. 5 is not a factor of 4 power n. Since 5 is not a factor of 4 power n, we will not get 0 for any possible value of n. So whatever you take n value, we will not get 0 because 2 is only the prime factor. To get 0, we need 5 also as prime factor. That is 2 into 5, 10. Then only we will get as last digit as 0. So this is not possible because 5 is not a prime factor. Okay, understood no? This detailed explanation I will give you later. This is clumsy, no? I will give it to you later. Next, Find the HCF of 96 and 404 by prime factorization method and find their LCM. Okay, this is the another example we will see here. Given numbers 96 comma 404. Here what it has written HCF. To get HCF, we need to take prime factors. For 96, what is the prime factors? 2 into 2 into 2 into 2 into 2 into 6. That is 2 power 5 into 3. For 404, 2 into 101. 2 square into 101. So by observing these two numbers, HCF is highest common factor. So first we need to check what are the common factors in this. Here 2 is the common factor. Here also 2 is the common factor. So 2 power 5, 2 power 2 are the common factor. And what is the HCF here? Two power 2. That is smallest of these two only we need to take. Okay, 2 power 5 and 2 power 2, we need to take the smallest number. Here see this HCF is product of the smallest power of each common prime factor. So product of, here common factor is only 2, smallest common factor. Smallest common factor means 2 power 2. Here no other factor is same, only 2 is there. In that also small is 2 power 2. So it is equal to 4. So HCF is equal to 4. And by using this, we need to calculate LCM. We know that HCF multiplied by LCM is equal to product of those two numbers. So here HCF is 4, LCM we need to calculate. Product of those numbers is 96 into 404. So LCM is equal to 96 into 404 by 4. 4 ones, 4101. That is equal to 96 multiplied by not 1. After this calculation we will get 96, and 96 is the LCM and 4 is the HCF. Okay. So if for any two positive numbers, the formula is here written. HCF into LCM is equal to A into B. Here we have given proof also for this. So if two numbers are given, then we can simply write here. HCF into LCM is equal to product of the numbers. Next we will see example 4. Here HCF and LCM of 6, 72 and 120 using the prime factorization method. So here for 3 numbers are given. Given numbers 6, 72, 120. So first we need to write the factors. 2 power 1 into 3 power 1. 72 is equal to 2 power 3 into 8, 9. 8 means 2 cube. 9 means 3 square. For 120, what are the factors? Two into 60, 2 into 30, 2 into 15, 2 into 3 into 5. Okay, so 2 cube into 3 into 5. 2 cube into 3 into 5. Okay, so first we need to take LCM. LCM means we need to write all factors, and when common factors are there, we need to write the highest factor. So here here 2 is there. 2 power 1, 2 power 3 and 2 power 3. So highest factor is 2 power 3 and 3 is there. 3 power 1, 3 power 2, 3 power 1. Highest factor is 3 power 3. Next 5 is there. 5 only 1 is there, so simply we write 5. So 2 cube 8. So 8 into 5, 40, 40 into 9, 360 is the LCM. Next HCF. HCF is the smallest common factor. So here in this 3, 2 cube, 2 and 2 power 3, all these are common. In this, what is the smallest? The smallest is 2. Next, what is the common? 3 is also common. 3, 3 square and 3. Okay? 3 square. In this also, what is the smallest? Smallest is 3. And 5 is not common. So, we will not write 5. So, we need to write common and the smallest. 2 into 3 is 6. So, HCF is okay. So, this we have calculated LCM and HCF. So, that formula what we have seen, HCF multiplied by LCM is equal to product of the numbers. It is only applicable for 2 numbers. For 3 numbers we will not write that formula is not applicable. Only if A and B are there, if only 2 numbers are there, then we can write HCM in LCM into HCF is equal to A into B. This formula is applicable. If A, B, C, 3 numbers are there, then we will not write HCM into LCM is equal to, LCM into HCF is equal to A into B into C. This is wrong. This is wrong. This is wrong. Only for 2 numbers we will write this. For 3 numbers, this is not the formula. That we will see later. Lastly, we will see that. Okay. Okay. Here some problems are there. Express each number as product of its prime factors. So I will write it fast. You can do it as homework. Here 2 into 70, 2 into 2 into 35, 2 into 2 into 5 into 7. So 2 square into 5 into 7. Second one is 156. 2 into 78. 2 into 39. 3 into 13. So 2 square into 3 into 13. Next for 3825. Here it is not divisible by 2. 3 into 1725. 3 into 3 into 425. 3 into 3 into 5 into 85. 3 into 3 into 5 into 5 into 70. So b square multiplied by 5 square multiplied by 17. Next 5005. Here 5 into 1001. 5 into 11 into 91. 5 into 11 into 7 into 13. So 5 into 7 into 11 into 13. Last thing is here 7429. It is slightly divisible by 'You can check it once. 7 into 19 into 23, these 3. That's it. You can check this one. Not sure, you do as homework. Okay, next problem. Find LCM and HCF of the following integers and verify LCM into HCF is equal to product of two numbers. Here 26, what are the factors? 3 into 13, 2 into 13. Next 91, 7 into 13. Okay, HCF means smallest common. What is common here? 13, and 13 is the smallest. LCM means 13 into 2 into 7. That is 180. So next 510 comma 92. 510. What are the factors here? 5 into 102. 5 into 2 into 51. 5 into 2 into 3 into 17. It's for 92. 2 into 46. 2 into 2 into 23. So here a square into 23. So for this LCM is, here 2 is common and highest is 2 power 2 and the remaining are not there, no common. So we write directly that is 5 into 3 into 17 into 23. So by calculating all those things we get 4690. HCF means what is the common? Common is 2 and what is the smallest? Smallest is 2. HCF is Next 336. 336 means 3 into 112. 3 into 2 into 56. 3 into 2 into 2 into 2 into 2 power 4 into 3 into 7. 54. 2 into 3 cube. Here LCM is equal to 2 power 4. 2 is common, highest is 2 power 4. Next 3 is common, highest is 3 cube into 7. We will get 3024. And HCF is smallest. 2 is common, smallest is 2. And 3 also common, smallest is 3. So HCF is 6. Okay. So here we got HCF and LCM. And by checking it, what we will get? HCM into LCM is 182 multiplied by 13, which is equal to 26 into 91. Okay, you can check it. Here you will get for both 2366. Here also HCF into LCM means 46920 multiplied by 2 is equal to 510 into 92. Here LCM you will get 23460. So here 23460 multiplied by 2. So answer we will get 46920 for both cases, this one and this. Here also 3024 is the LCM multiplied by 6 HCM is equal to 336 into T4. For both you will get 18144. 18. Okay. Here for two numbers we have calculated the LCM and HCF and their product also we calculated. And find the LCM and HCF of the integers given above. Okay, this you calculate and tell the answer in the comments. Okay, this I will given as homework. Next, given that HCF is 306, HCF of 306 comma 657 is equal to 9. Find LCM. Here two numbers are there. We will write the formula LCM into HCF is equal to product of the numbers, that is 306 multiplied by 657. Okay, this is the formula. What given? HCF is given, and these two numbers we know. We need to calculate LCM. So LCM is equal to 306 multiplied by 657 by HCF. 306 by 9. 9 3 is 27, 9 4 36. We'll get 22338 is the LCM. So the LCM is equal to double 2 double 3. Okay. So here check whether 6 power n can end with a digit 0 for any natural number. Here we have seen for 4 power n. Same thing. We have given for 6 power n. So 6 power n means 2 into 3 whole power n. So 2 power n into 3 power n. These are the prime factorization of 6 power n. Prime factorization of 6 power n. So 6 power n to be having last digit as 0, it should have a factor of 5. Factor of 5. Because 2 is already a factor. 6 is equal to 2 into 3. So 2 is already factor. To get last digit as 0, we get 2 into 5 means 10. Then only we will get last digit as 0. So what to get 0 as last digit? 5 as the factor of 6 power n. But here 6 power n is equal to 2 power n into 3 power n. But 6 power n is equal to 2 power n into 3 power n. By uniqueness of fundamental theorem, only 2, 3 are prime factors of power n, and 5 is not a factor. So there is no possibility to get last digit of 6 power n is to be 0. Okay. So what we need to write first, what is the factorization of 6 power n? Factorization of 6 power n is 2 power n into 3 power n. Okay. Last digit to be 0, it must be multiplied with 5. That means it is having a factor of 5. But by this factorization method, the uniqueness of fundamental theorem, what it says, only 2 and 3 are factors of 6 power n. No other prime factor can exist for 6 power n. If only 2 and 3 are prime factors, 5 is not a factor. So if 5 is not a factor, there is no possibility to get last digit of 6 power n to be 0. Okay. Understood now this problem. Next, explain why 7 into 11 into 13 plus 13 and 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 are composite numbers. So here we need to calculate what are these numbers and is that are composite numbers or not. Composite number means it can be expressed as unique way in prime factorization method. 7 into 11 into 13 plus 13. So here 13 is common in both cases. 7 into 11 plus 1. So 13 into 7 into 11 is 77 plus 1. So 13 into 78. 13 into 2 into 3 into 30. 78 can be written as 2 into 3 into 13. So here it is 2 into 13 into 13 square we got. So this first one is what we get prime factorization of 2 into 3 into 13 square. So it can be called as a composite number. Next one you see 7 into 6 into 5 into 3 into 2 into 1 plus 5. Here in this 5 has common in both. 5 into 7 into 6 into 4 also. 4 into 3 into 2. 1 is there or not? No. So 5 into calculate what you will get. 7 into 6, 42 into 4 into 3 into 12 into 2, 24 plus 1. So 5 into 42 into 24. Okay, we got 1009. Now we will do prime factorization for this and write in comments. We will check whether it is a composite number or not. Okay. Next, here in this topic we have the last problem. In a circular path around sports field, Sonia takes 18 minutes to drive one round of field, while Ravi takes 12 minutes for the same. Suppose both start at same point at the same time and go in some direction, then how many times will they meet again at the starting point? This is a simple calculation of LCM. What it has written, Sonia started at this point and Ravi also started at this point, and they are moving in same circular path, same path. Okay, so I write this is the path, both are starting here, Sonia and Ravi. So here Sonia is taking 18 minutes to complete and Ravi is taking 12 minutes to complete. 18 minutes and 12 minutes. So they started at same point, then after how many minutes they once again came to same point. For this type of calculations, simply we need to write LCM, because least common multiples. Least common multiple means, suppose if they start at starting point, what is the next multiple of this 12 and 8? They will get at that point only, they will meet again. So LCM of 12 and 8. So for 12, what are the factors? 2 power 2 into 3. For 18, 2 into 3. So LCM is equal to 2 square into 3 square. 4 into 9, 36. So after 36 minutes, they will meet again. So let's check this. So first Sonia, 18 minutes, he got one round, and 36 minutes means another 18 minutes. 18 into 2, 36. So he got at the starting point. And Ravi means, Ravi in 12 minutes he completed the one round. So first 12 minutes one round, second 12 minutes one round, third 12 minutes another round. So 12 into 3, 30, 36. So in 36 minutes, Sonia completed 2 rounds and came to same point, and Ravi completed 3 rounds, came to same point. So for this type of problems, simply we need to write LCM of those two numbers to get the same starting point for both. Okay, understood, no? So here we have seen a lot of problems, a lot of examples, and 2 theorems we have explained. Everything understood. Now if any problem, any confusion is there, please write in comments. I will try to explain one side. No issue. Okay, thank you friends. Please like and subscribe my channel. Okay, thank you.